Okay, so I think it's time to start. Let me first welcome everybody for this third edition of the Stochastic Thermodynamic workshop. I will take the opportunity to thank all the organizers for doing this wonderful job. We will immediately start the meeting with Masahito Ueda, who's going to talk about universal thermodynamic uncertainty relation in non-equilibrium dynamics. Masahito, the floor is yours.
Okay, thank you very much for the introduction. So first of all, I'd like to thank the organizers for the kind invitation. It's really nice to see many of our friends, albeit online. So today I'll be talking about our recent work on universal thermodynamic uncertainty relation in non-equilibrium dynamics. The main player of this work is Liu Ziyin. So this is the outline of my talk. I will introduce TUR and review some background information needed to discuss our main result. I will then present our main result, Universal TUR, and discuss two applications about the measurement accuracy in physics and the fundamental bound on theoretical finance. Finally, I conclude my talk and speculate some further applications of our work. So thermodynamic uncertainty relation concerns a trade-off relation between the average and the variance of a current and entropy production in a stochastic process. A physical interpretation of this TUR is that the measurement accuracy of a thermodynamic current, which is given by the right-hand side, is bounded from above by the entropy production of the system. However, the original TUR can be applied only to observables that are anti-symmetric under time reversal, and also to steady states and to a linear response regime. So in this talk, we attempt to derive a universal thermodynamic uncertainty relation that is applicable to an arbitrary observable of both physical and non-physical systems that can be far away from equilibrium and yet contains only quantities that appear in this original thermodynamic uncertainty relation. So how this relation should be extended if we are to achieve this goal is the main subject of this talk. So before presenting our result, let me review some background information for our study. A key quantity in stochastic thermodynamics is the trajectory-wise entropy production, delta S. We consider a discrete time Markov process between time step 1 and time step tau. The time evolution of the system is completely specified by this stochastic trajectory of state X and probability distribution. The time reverse trajectory and the probability are also given by this expression, and the trajectory-wise entropy production is defined by this equation. The trajectory-wise entropy production has the following important property. So number one, it is zero if and only if the forward and backward trajectories share the same probability. That is, the state is at equilibrium. Number two, it cannot decrease on average, which is consistent with the second law of thermodynamics. And number three, it can be decomposed into the system's entropy change and heat, which is nothing but the detailed fluctuation theorem. The detailed fluctuation theorem, given by this, usually requires the dynamics to be stochastically reversible. in the sense that to any backward path here, which is non-zero, correspond to a forward path, again with non-zero probability, and vice versa. So there is one-to-one correspondence between forward and backward probabilities, processes. And usually if the forward probability vanishes, so does the backward probability and vice versa. However, if some forward probability path vanishes and the backward probability doesn't, like this, then the path is not even stochastically reversible, but absolutely irreversible. So absolute irreversibility causes a negative entropy divergence and integral fluctuation theorem to break down. So in the presence of absolute irreversibility, a generalized master fluctuation theorem holds, described in this paper. And we first define the entropy production of a forward process P and against an arbitrary reference dynamics Q as follows. Then the generalized master fluctuation theorem gives the following equality for an arbitrarily observable F. So F times exponential of this probability of this quantity R is given by gamma times F. Here, this symbol means that this F is averaged over the reference dynamics path whose forward probability is non-zero. So if Q is chosen to be the time reversal path, then one obtains this equation. And if F is equal to 1, then one obtains this generalized integral fluctuation theorem. The point is that the right-hand side is not necessarily equal to 1 due to the presence of absolute irreversibility. Here, gamma on the right-hand side represents a degree of reversibility. If gamma is 1, as is usually the case, then the system is fully reversible. But if gamma is equal to 0, then the system is fully irreversible. An example of system with absolute irreversibilities include, for example, free expansion, unidirectional dynamics like diode, and systems with systems with absorption states. So these systems often appear in many non-equilibrium situations in physics and elsewhere. Now we are ready to introduce our main results, the universal TUR. So our main result is a universally applicable TUR, and shown by this equation. Here, this quantity QP again shows the average is taken over the reference path Q corresponding to the non-zero probability of the forward path P. So there are two key features. One is that this formula is universally applicable to an arbitrarily observable F of an arbitrary Markov systems. And actually, this achieves two types of optimality. That is, for any system, there is at least one observable that saturates a bound. And for any observable, there is at least one system that saturates a bound. The proof is somewhat technical, and please refer to this reference. So in the absence of absolute irreversibility, that is a case of gamma equal to 1, our result takes this simple form. So if we further specify that Q is equal to the time reversal path of the forward path, then we have the following relation, which is physics relevant formula. So when the system is in a steady state, and when F is a thermodynamic current, which is anti-symmetric with respect to time reversal, then we have this formula. So expanding the exponential term to linear order in entropy production. Then we recover the familiar TUR. So new generalized TUR is in the first expression where entropy production appears in the exponential form. And furthermore, if F is not necessarily physical, then the more general formula is given by this expression. And this expression can be applicable for systems outside of physics. And when in the presence of absolute irreversibility, then this more general formula should apply. Okay. So our main result is a direct consequence of this general fluctuation theorem derived by Murashita. And proof of our TUR is rather simple. For an arbitrarily observable F, generalized fluctuation theorem shown in this formula implies the covariance relation. So covariance of F and exponential of E to R is given by this. And since the first term on the right-hand side is given by this master fluctuation relation, and since exponential to the R is given by just gamma, so we have this relation. Furthermore, the Cauchy-Schwarz inequality states this one, where the variance is calculated by this. Therefore, we obtain this final formula. So now we discuss two applications of our main result. One is a bound on measurement accuracy in physics, and the other is a fundamental bound in theoretical finance. So I took this example because I wish to demonstrate that our TUR can be applicable to subjects beyond physics. So we first apply our TUR to set the bound on measurement accuracy of a thermodynamic current. So as a reference dynamics, let us take this form, namely the initial distribution of a reverse dynamics is the same as the initial distribution of the forward dynamics. So furthermore, if F is a thermodynamic current, I mean anti-symmetric with respect to time reversal, then our TUR leads to this formula. So now the right-hand side is a measurement accuracy because it's a mean value divided by the variance. Notably, the left-hand side includes not just the entropy production, but also the quantity D. D is just the ratio of this probability. So it's this formula. So the physical meaning of this D may be understood as follows. So when the system is stationary, the final distribution is the same as the initial one for all trajectories. Therefore, this logarithmic should vanish and D is equal to 0. Thus, D may be regarded as a degree of non-stationary. So if it is completely stationary, D is 0. But if it is non-stationary, D in general can be positive. So far from equilibrium, the entropy production and the degree of non-stationarity together determine the bound of measurement accuracy of a thermodynamic current. So this is one main message. So far from at steady state, entropy production governs the bound. But if we move away from stationarity, then not just entropy production, but also this degree of non-stationary quantity play a crucial role. So when the system is now close to a steady state, then D is negligible, and one can show this approximate relation, namely the bound on measurement accuracy increases as the entropy production is increased, as expected. In general, however, this exponential term is system dependent and can actually decrease with increasing entropy production. So let us now demonstrate these findings with numerical simulation. So we consider the simplest system, that is the transition dynamics of a two-state system, A and B, with symmetric transition probability. So PAB is equal to 2PBA. But we take initial state to be far from equilibrium. That is, probability of A is 90%, probability of B is just 10%. And the stationary distribution is, of course, a uniform distribution and satisfies the detailed balance condition. So the observable we consider is a thermodynamic current and run the simulation for different transition rate. So for a thermodynamic current, the standard TUR can be written in this common form. So variance of F is larger than some quantity Q. And Q takes a different form for different TURs. So listed here. So we say that bound is good if Q is close to the variance of F. So this right panel shows plots Q for several different bounds as a function of the transition probability. So note that this black curve shows the variance, and the other dots shows different variants of TUR. So we note that original TUR Q steady state and discrete time TUR QPB actually violate the inequality because those two curves are above this black curve. So since it's above, so it violates this inequality. However, both our results Q hours and Q hours of Q and the results of Liu obtained by Liu et al. Satisfies the inequality. Moreover, our result is much tighter and agrees better with the result of numerical simulation. So notice that again, this black curve is the variance, and closer to this variance from below is a better approximation. So now the first hours is simply includes entropy production, gives this curve. So which is below this variance, but a little bit far below. But this Q hours of Q, which increases the degree of non-stationarity D, agrees much better with this accuracy. So our result is gives much tighter and agrees better with the result of numerical simulation. So our TUR shows that the bound on measurement accuracy involves not only entropy production delta S, but also the degree of non-stationarity D. So there are three panels, and the leftmost panel shows this bound agrees in trend and magnitude with accuracy, and therefore provides a good measure for bound on the measurement accuracy. However, the middle panel shows that this bound shows non-monotonic dependence on entropy production, and the rightmost panel shows that accuracy also depends non-monotonically on entropy production. Thus, the entropy production alone is not enough, and the degree of non-stationarity is needed to give a reasonable bound on measurement accuracy. So this panel shows the relevant quantities appearing in our TUR against the transition probability P of AB. So we see that our bound closely follows the measurement accuracy. So this measurement accuracy is this black, this one, squared one, and our result follows very closely to this measurement accuracy. And the other two plots entropy production and the degree of non-stationarity. So there are regimes where delta S dominates, or other regimes where degree of non-stationarity dominates. Therefore, both delta S and the degree of non-stationarity can play important role in determining the bound on measurement accuracy. So physically speaking, if we move away from stationary current, then this degree of non-stationarity term plays a crucial role. But in the usual case, if we discuss the stationary situations, then we can just forget about this D and consider only entropy production delta S. Okay, so to demonstrate the applicability of TUR beyond physics, we now wish to apply it to problems in theoretical finance. So applying our TUR here, we take the general formula where we do not assume that F is anti-symmetric with respect to time reversal. So we apply our TUR to the financial return of any investment strategy. Then we obtain a lower bound on the return volatility. So in theoretical finance, variance or standard deviation is called volatility. And so our TUR gives the volatility is lower bounded by this quantity. So interestingly, the physical entropy production delta S can thus be linked to the volatility and return of any financial asset. So also note that previous TUR cannot apply to this type of problems because R is not a thermodynamic current. So R is not anti-symmetric against time reversal. So the previous TUR cannot be applied to this situation. So we next apply our TUR, again, this formula, to the financial return, and now choose the reference dynamics to be any stochastic process with the expected return equal to the risk-free rate. So in the financial sector, risk-free interest rate is actually the interest rate of the treasury bond, US treasury bond. We then obtain this formula where the chi is a fluctuation of return against risk-free rate divided by the volatility. And this quantity is called the Sharpe ratio. So the good investor has a higher Sharpe ratio. And And this is a fundamental quantity that characterizes the performance of any investment strategies. And this agrees in form with a celebrated Hansen-Jagannathan bound. The Hansen-Jagannathan bound is nothing but this formula. But we would like to emphasize that our bound is technically more general than the original Hansen-Jagannathan bound, because the original bound requires Q to be a martingale. So we didn't assume such martingale assumption and derive this formula from a more generic point of view. So the derived bounds can be used to check the validity and the correctness of economic theories against observable data. For example, take the above derived bound as an example. So this formula. In general, for any theoretical dynamical model of the financial return, so in the theoretical finance, calculating the financial return is the foremost subject, and they usually calculate financial return in the future on the basis of Black-Scholes equation, where the volatility is a key quantity. Now, R star and this exponential minus 2 times entropy production can be calculated from such theory. And actual R and volatility can be estimated from the actual data. Then, by plugging those numbers into this formula, and if they are consistent with this formula, the theory is okay. But any violation of the bound can be utilized to reject the incorrect economic theories. In fact, most economic theories violate this inequality. So we can reject those theories. And the original HJB is also designed for this purpose. And in this derived inequality, the entropy production, which appears in the denominator, is we can say much better understood in physics compared with a rather vague martingale measure, which the original HJ envisaged. So this presents an interesting example of utility of physics to theoretical finance. So I think we can consider the notion of entropy production in price action movement. So to summarize, we have derived a universal TUR that can be applied to any observable, making it relevant to any field that involves non-equilibrium dynamics, such as biology, machine learning, and finance. The derived bound sheds new light on the role of degree of non-stationarity in determining the bound on the measurement accuracy. And the derived TUR unifies the physics TUR and the celebrated fundamental Hansen-Jagannathan bound in theoretical finance. And besides the degree of reversibility gamma, the universal TUR only involves simple quantities that appear in the original TUR, F, delta S, and variance. So I wish to conclude my talk by making some speculations about possible applications of a universal TUR. So first, cosmology, because free expansion is important here. And second, machine learning, because key quantities such as generalization error is not a thermodynamic observable. And third, biology and ecology, because involved processes are naturally far from equilibrium. So this is all I wish to discuss in this talk, and thank you very much for the kind attention.